All right, so in class on Friday, we talked about changes, right? And one thing we learned was how do we compute the change in variable? How do we compute the change in a variable? Where is Morgan Delgado? Where's Morgan? Okay, make sure you're responding. Where's Prakar? Praveen? Yeah. Oh, you can remain sitting. That's fine. Do you remember how we said we computed? Good. All right. So the change in a variable we know is the final value minus the initial. This should make perfect sense, right? So if you started off with 3 gigabytes on your smartphone being used up, and then you ended up at 5.5 gigabytes being used up, how would you compute that change? 5.5 final minus initial 3, which would give us the change of 2.5. So this equation, we want to, yes, memorize it, but yes, fully understand it, so you don't even have to memorize it. It should just be like falling out of bed, right? So it should make sense. Okay. But now suppose that y changes along with x in some sort of relationship. Y and x are in relationship with each other. Then we have a way of determining dy in a different way. Not by final minus initial, but determined based on dx. So if dx changes a certain amount, based on that amount that it changes, we also want a way to calculate how much y changed, rather than the final minus initial way. So what principle does this have to do with? Figuring out what dy is based on dx or given dx. What is that about? Yeah?
Rates of change.
Okay, so you read it and specifically, what kind of rate of change?
Constant.
You should have read in your reading. This is all about constant rate of change. So constant rate of change now is about determining a change in a variable based on the change of another variable instead of final minus initial. Okay? So let's talk about that. So we're going to use dx to determine dy. Okay, so you're using your car's cruise control and you're traveling at 70 miles per hour on a flat, smooth highway. What is the meaning of 70 miles per hour, the constant rate? So this number, 70, what does that number 70 mean? Yeah, Aiden.
The amount of miles traveled in 1 hour.
Okay, so he said that every additional hour means you travel 70 additional miles. Is that right? Is that what that means?
Yeah.
Does it mean any more than that?
No.
Yes.
Oh, yes. This is a very narrow meaning. We're going to find out. So you all know that it's a narrow meaning. You just don't know that you know. Okay? Going 70 miles an hour tells us a lot more than this. It tells us a lot more than in 1 hour you go 70 miles. See, I'm going to show you. You know a lot more. Because you know how far you go in 2 hours. How far do you go in 2 hours? See, you all answered. I told you. All right? And you also know how far you go in 5 hours. How far do you go in 5 hours? 350 miles. You also know how far you go in half an hour. 35. And then you know how far you go in a tenth of a mile. Do you know any more than that?
Yes.
We could just keep going. I could just give you these additional time amounts over. I could give you any number of those, and you could tell me how many miles you would travel at 70 miles per hour. So really, 70 miles per hour means that given a change in time, and that's what that's dx. For any change in time, what's the change in distance? So look at what are you doing every single time? Given a change in time, your change in distance, volunteer, is what? How do we get that change in distance given any change in time? Yeah?
For every 1 unit of time that you change, your distance changes 70 miles.
No, but so the point is that there's all these different units of time that we could change. Okay? It's not just 1 unit of time. For any change in time, 2 hours, 5 hours, a half hour, a tenth of an hour, how do you get the change in distance? Yeah? Multiply by 70, right? Every single time, you just multiply by 70. So for any change in time, the change in distance is 70 times that change in time. So rather than our every hour means 70 more miles, we want a much better meaning for this. For any change in time, the change in distance is 70 times as much as the change in time. And you knew that. You all answered those questions. You just didn't know that you knew that, right? Yeah.
Are you recording?
Yes, I am. Thanks. Does it make sense? Huge, huge principle we're going to see in the next month and all the course, but especially as we're building up to a big idea in the next month or so. This is a huge idea. Burn it in your brain. We're going to practice it over and over and over again, but just burn it in your brain now. That a constant rate means more than just that you have that much change in one unit of change of x. It means that given any change in x, the corresponding change in y is that rate times as much as the change in x. In this case, for any change in time, the change in distance is 70 times the change in time. Super important. Super important. Okay, another example. Gas is $2 a gallon, based on a true story, right? Gas is $2 per gallon. What is the meaning of $2 a gallon, the constant rate? Where's Josh? Tagunga? Joshua? Yes, sir. Give it a shot. What does it mean that gas is $2 per gallon?
Where every single gallon costs $2.
Okay. For every single gallon, it costs $2. What do we think? Every additional gallon means $2 more in cost. What do you think of that? Michaela Sanchez. You like it? Okay, so yes, right. This is a narrow meaning. Can you give me a better meaning?
For any additional gallon, the cost is 2x.
Okay, good, yeah. So really, for any change in the number of gallons, so not just one more gallon in your tank, any amount of gas you want to put in there, you know how much the cost goes up. How much does the cost go up? Not $2. 2 times as much as your change in gallons. So if you put in 10 more gallons, how much does your cost go up?
$20.
You multiplied by 2, $20. If you put in a half a gallon, how much does your cost go up? $1. For any change in the number of gallons, the change in cost is 2 times that change in gallons. So this is a broad, strong meaning for that value of 2, the constant rate of change. So this equation gives us, the meaning of this equation gives us this strong meaning for what that 2 means, that $2 per gallon. Given any change in the number of gallons, the change in cost is 2 times that number of gallons. Doesn't make sense. Whenever we use these symbols dx and dy, it implies that we have constant rate of change. We'll always be talking about constant rate of change whenever we're using dx to mean a change in x and dy to mean a change in y, and we're using those in a relationship, that will always mean a constant rate, and we'll always have this form. Okay, so let's practice. So a store sells make your own snack mix gifts. The box costs $B and the snack mix costs $2.75 per pound, which means, tell your neighbor, what does that the snack mix costs $2.75 per pound. What does it mean? Practice, tell your neighbor. Go. Okay. Let's regroup here. Where is Kyle Klein? In the corner. Okay, hold on. Here we go. What'd you say? What's the meaning of $2.75 per pound?
For any change in the number of pounds, the cost is 2.75 times the number of pounds.
Okay, so what is 2.75 times the number of pounds? Almost the change in cost. Yeah, so he said for any number of pounds, the additional cost that you'll pay is 2.75 times that number of pounds. Okay, so that's what you should have said. Or something like that. There's many ways to phrase it, okay? The exact words are not critical. The idea is the critical thing. So there's many ways to phrase this. Many ways to phrase this, okay? So we want to define these variables in this situation. So what I want you to come up with is phrases, written English phrases that describe what each of these is. Okay? So x is what? Y is dx, dy, and m. Okay? In this situation. So I'm not looking for values. I'm looking for written definitions of each of these in the context. So maybe let's do the first one together. What is x? X is the number of pounds of mix that you're going to buy. Okay? So the number of pounds of mix is x. So from there, define what y is, dx, dy, and m. Take a couple minutes. Work together if you need to. Ask if you need to. Okay? Go. One-word answers are not sufficient. You need a whole, thorough, specific phrase. Okay. Where's Kaylee Sanson? Kaylee, how'd you do? What'd you say that Y was?
I said Y is the amount of money spent on the snack bag.
Okay. The cost of the gift. All right. What she said, yeah, she said the amount of money spent on the snack gift or snack box, the cost of a gift, and then specifically with X pounds of mix in it. Okay. And then that cost is in dollars. Okay. What would you say DX was, Kaylee?
I actually didn't get the
Okay. So given a variable X, what is the meaning of the variable DX? Where's Marisol Sanchez? Marisol, what would you say DX was? Change in pounds of mix. Good. Change in the number of pounds of the mix. So that goes back to Friday. So the difference between a variable and a change in that variable. Right? How much space of memory is taken up in your smartphone versus some change in that amount of space. Really got to have a strong concept of that. DX is a different animal than X. X, you think of starting from 0 and taking on a total value of a quantity. DX is any change in that value. Okay, DY. Also, Marisol. The change in cost of the gift in dollars. Okay. Again, there would be half a dozen different ways to phrase these that would be correct. So don't lock in on a certain wording, right? Ideas are more important than specific wording. Okay. All right. What is M? Where's Annabelle Judd? Okay, it's right. So it's that 2.75 number, and what do we call that number? Do you know? That's the constant rate of change. and it's 2.75. Now I should have my units on here. So dollars per pound. That's supposed to be a dollar sign. Okay, $2.75 per pound. That's the constant rate of change. Okay, so I want you to write an equation using these variables, some or all, or that computes the constant rate of change. How would you use these variables to compute the constant rate of change? So if it's an equation, it's going to start as m equals. What would compute that constant rate of change? M equals what? From your reading. Yes, sir.
dy over dx.
He wants dy over dx. Agree? That's it. So if you took the change in y divided by the change in x, you would get that number 2.75. And so it could be any change in x and its corresponding change in y, right? Any change in x and its associated change in y, that ratio would be the value of m. Okay, how about write an equation using these variables that would compute the change in cost for a change in the number of pounds bought. I want you to do this all by yourself. Okay, so write an equation using these variables that computes the change in cost for a change in number of pounds bought. Take 30 seconds to do that. Everyone do this and get it. We've got to get this right. An equation that computes the change in cost for any change in number of pounds. I'm going to call on someone in about 20 seconds. Okay, where's Kyle Acacello? Oh, that's you.
Basically came up with dy equals
So-
2.75 times dx.
This is what he's suggesting. dy equals, you said,
2.75
so we're going to use the variables only.
m times dx.
He wants dy equals m dx. Agree? You should all agree. That's what you should add, right? So given any change in number of pounds, the change in cost is 2.75 or m times that change in pounds. This is the big point for today. The meaning of m. The meaning of m is defined in this equation, or this relationship is how we frame and understand what m is, through that equation. Okay, so after scooping some mix into your box, you decide you want more. The additional cost you will pay for 1.5 more pounds of trail mix is 2.75 times $1.5. So now we've defined the meanings of all these. I want you to write the values of these in this particular situation. So I got a particular situation. What's dx? What's dy? What's m? What's x? What's I? Go. Y. Go.
Are you buying 2.5 pounds or 1.5 pounds?
So you have some mix in your box, and you're going to add in 1.5 more pounds.
It's the last one. So what does dx? This one.
Okay, where's David Lucero? David. Oh, right next to him. All right. What did you say the value of dx was?
I said that it was the 1.5. It was plus the initial minus the initial. So because you need the final amount minus the additional amount. So, wait, so.
Do I need to do a calculation here? So it's just asking, given this situation, what is dx?
Like, are we assuming that we started with, oh, it's just 1.5, sorry.
1.5. What?
Ah,
After some deliberation, he said that dx was 1.5 pounds. Agree? This is the change. This is the change. So let's go to x. So from here, let's jump to x. What's the value of x? Yeah?
1.5 pounds.
1.5 pounds. Agree? Aiden? It's the initial amount. Well, I want to write down a number.
How much is already in the box?
What is x? We don't know. We don't know how much additional there was. All we know is that the final amount is 1.5 more than that. There's not enough information. You don't know the total pounds because you don't know how much you started with. You don't know how much you finished with. All you know is that you increased it by 1.5. The change was 1.5. Make sense? Okay, dy. What is dy? Robert Crutcher. Where's Robert? Yeah. Okay. Where is Anna Vaughn? Anna here? Anna Vaughn? Oh, sorry. What'd you say dy was? Change in the cost. And do we have a number for that? Do we know what that number is? Yeah.
$4.12.
And how'd you get that?
I multiplied 1.5 times 275.
Right. And that was actually exactly what I gave you. So we know dy equals mdx, which is our 2.75 times 1.5. And you got 412, is that right?
Yeah, and a half cent.
Of course the store is going to charge 413,
Yeah, of course.
right? Okay. Does that make sense? Is that how much it went up when we added 1.5 pounds? That's how much the cost went up. What is the total cost? We don't know. We don't know how much it was to start with. And so we know how much it went up. It went up $4.13, but we don't know what the final or the initial value were. So we don't have any value of X or Y. What about M? Still our $2.75 per pound. So we're working on this because calculus involves lots and lots of symbols and notation applied to real-world situations. So that's why we're working on this. Can you read a situation about rate of change and different quantities changing together and assign good variables and notation to mean things in that situation, because that's calculus is loaded with that. All kinds of equations and expressions of notation that have meaningful representation in the context, and you have to have that. You have to have that ability to transition between understanding the situation and the symbols that represent it. Okay, that's why we're practicing this. How about this? Next year, move 0.4 pounds from your bag. Return it to the bin or your box, whatever. Okay. So what are these variables in this situation? Okay, where is Autumn? Autumn. What did you say dx was? The value of dx, or change in number of pounds. She wants negative 0.4. How can you have a negative number of pounds? It's a change, right? So it's okay, a negative number of pounds is possible because, in this case, because it's a change, meaning that the number of pounds went decreased, right? Decrease would be a negative change. You should have seen that in your practice in your homework, right? You saw lots of situations where you had changes in a variable that were negative because the variable, the value of the variable, decreased. Okay? Corresponding dy. Where is Hannah Lou? Hannah. Yeah. She wants 3.75 times what? 2, thank you. 2.75 times negative 0.4, and just, could I just stop there? Is it valid? It might be uncomfortable, but it's valid. This is the same as, so representing it this way is valid. Now, it's not the way you talk in the store, right? In the store, we would say what? What did it turn out to be? What is that? I know someone punched it in. Tell me. $1 what? 10? So your cost went down $1.10, so that's a change or a negative dy. dy that's negative 1.1. But for our purposes, this is a totally valid representation of that dy. It's the product of 2.75 and negative 0.4. It actually it has an advantage. What is the advantage of representing it that way? Yeah, you can see the guts of it, right? You can see where that dy is coming from. We see that it's m dx. M dx, okay? All right. M is now negative 2.75?
No.
Still positive. Still represents an increase of pounds. Means an increase in cost. X and Y? Still don't know what our, how much. We don't have anywhere along the way here that we know exactly how many pounds we've taken or that total cost. We just know about the change. Okay. Any questions on defining variables in real-world situations, which is going to be crucial. If calculus is about modeling real-world situations and how different quantities are changing together, we need notation and symbols to do that. You've got to be good at that. All right, let's skip ahead to this example. Let's do a little bit on this. We'll go back to it. We'll do another one of those on Friday. We'll do more practice of that stuff on Friday. So let's change gears just a little bit here. Suppose you open your laptop during class to take notes. 35 minutes after class, your laptop battery has a 41% charge. 75 minutes after class has started, the battery has a 28% charge. The percentage charge, P, which is our dependent variable, changes at a constant rate with respect to the number of minutes since class began, which we'll call T, and that's our independent variable. Okay. Don't do any count. So just work through these 4 questions. Okay, work through these 4 questions. Do that, and then we'll regroup. Okay. Here's the big thing for today. This question right here. The answer to that question is the most important takeaway from today's class. Okay, so you should come up with that unit is percent per minute. So if its value is m, we're not figuring it out for now, but we'll just call its value m, percent per minute. What is the meaning of that value of m? One last time. Who's got it? In the back, yeah.
The constant rate of change.
It's the constant rate of change. And so what is the meaning of that number m? What's the meaning of that? Somebody knew. Go for it, yeah. No, the meaning of the value m. This is our big thing that we worked on today. Yes, sir.
Constant rate of depleting percentage.
Right, but what's the meaning of that number? That's what we call it. We call it the constant rate of change. What's the meaning? Yes, here in the yeah.
For any change in minutes, you can
To get. Okay, so everyone get this. This is what we worked on hard today. For any change in minutes, she said you can multiply it by m to get the corresponding change in percent. For any number of minutes that goes by in class, when you multiply it by m, so what's their equation for this? If it was p and t, then what equation do we have? dp equals m dt. For any number of minutes that goes by in class, the change in percent would be m times that constant rate times as much as that change in minutes. This is the big takeaway today. We're going to see it over and over again. Super, super important. Was there a question over here? Did you have a question? Yeah.
Oh, a stretching.
Okay. All right, so as your packet